Okay, I shan't detain you for long. There's an old news saying, give a medalist a minute and they'll take an hour. So I'll just try and give you some idea of what's, I think, new and exciting about igneous geology. And there's a mention of the subsurface that we heard in the last talk, and I think that integration of geophysical images of the subsurface with our understanding of how volcanoes work is a really exciting new development in igneous geology. I work on volcanoes currently. This is a volcano that I'll talk a little bit about. This is in the Bolivian Altiplano. This is called Uturuncu, and it's just 6,000 meters tall. So it's a bit breathless at the top. The reason this is an exciting time to be an igneous petrologist is that there's a real sea change in the way we understand igneous systems. The defining paradigm for a century or so was the idea of a liquid-filled vat, a magma chamber, at some relatively shallow depth beneath a volcano, in which all sorts of crystallization and differentiation occurred, dense crystals settling to the bottom, light gases leaving from the top. There are all sorts of reasons that I haven't got time to go into why that paradigm no longer really works. And we're starting to see igneous systems as trans-crustal in their extent, and involving not liquid vats, but partially molten systems in which the melt is distributed along grain boundaries. And for most of the lifetime of these systems, the proportion of melt is of the order of 10 or 20%. Sure, magma chambers exist, but they're ephemeral, they're transitory, and they're not very easy to image geophysically because they're probably relatively small. So there's a kind of a shift from here to here, this trans-crustal magmatic mush, and I'll just show you a number of examples. So this is, here is that volcano Uturuncu that I showed you in the opening slide, and this is this is a map of South America. This is Argentina, Chile, Bolivia here. Uturuncu is somewhere around about there, close to the triple point of those three countries. And Uturuncu overlies the largest underground body of partially molten rock that we've ever seen. And this is an image, this is the surface, this is the depth below sea level, and this is the resistivity. So it's just another geophysical technique, in this case measuring resistivity or conductivity of rocks. And where you have partial melt, or indeed where you have any conductive fluid, you get reduced resistivity, which is red on this image. And you can see under Uturuncu is a whopping great red blob, and we interpret that as a partially molten region. It's about 500,000 cubic kilometers, and it's at depths of 12 to 17 kilometers. And what's exciting about it is it contains not a huge amount of melt, proportionally about 20%, but that melt has about 9% of water dissolved in it. There's actually, in this body, there's an entire dissolved Lake Superior dissolved in the melt underneath the Altiplano. This is just one example. This is a real whopper, if you like. But we see similar images. Here's the Cascades. This is Mount St. Helens here. Someone talked earlier about a seminal event that was inspirational. This volcano erupted in a quite iconic fashion in May 1980, which is when I first started being an undergraduate. That was a good launch, really, for petrology. So here's Mount St. Helens. Here, this is a section from west to east, a couple of Cascades volcanoes, St. Helens and Mount Adams. This is again a conductivity or a resistivity image. Resistive, conductive stuff or low resistive stuff is in red and yellow. And here is this deep reservoir of partial melt, and it's connected to the surface along a couple of pipes, one beneath Mount St. Helens that is relatively recently been active, and one of the Mount Adams that is not currently active. And this region here is a region that I've enlarged there. There's the volcano, and we seem to have some transfer zone where melt comes out of these deep reservoirs and ascends and fuels volcanism. And so what we want to understand now in terms of anticipating eruptions is, why does melt leave its deep storage zone and rise up beneath the volcano? And we can see images like this in almost every volcanic setting, not just subduction zones like these, but also rift zones in continental interiors. So we know a little bit about the ascent of magma beneath Mount St. Helens. So this is some work I published a few years ago. This one, Madeline, are you still here? No, this was my former PhD student and I produced this paper. So what we were doing is we were looking at little trapped droplets of melt inside crystals. The thing about volcanic eruptions is all the gas that we know was once present, that 9 or 8% water in the melts beneath the altiplano, it's gone on eruption. So if we want to know how much water was in the magma before eruption, we look at these little trapped globules of melt. We call them melt inclusions, and they haven't lost their gases. And so we analyse these little fellas. They're probably, you know, a hair's width across, 30, 50 microns, something like that. And we can measure the water, and a couple of interesting things emerge. This is the water content that I've measured in hundreds of these, and this is the silica content, and that's really just a measure of crystallization. Crystallization drives you that direction, and we'll ignore the melt inclusions that seem to have burst there in the grey field, but by and large, as crystallization proceeds, the water content goes down. What drives magmas to crystallize when they have water is not cooling, as you might imagine. It's actually just the loss of water, and the loss of water occurs because the pressure drops. So when magma ascends, if it's got water in it, it sheds the water, and that drives crystallization. They don't need to cool at all. In fact, rather surprisingly, this is the same plot. This is pressure. If you want to turn this into depth, that would be about 8 kilometers, and that would be the surface. As the pressure drops, the magma actually gets hotter. The magma gets hotter because the driving force for crystallization is the loss of gas, and the loss of gas drives crystallization. Crystallization releases latent heat, and latent heat makes the temperature go up. So actually decompressing magmas crystallize and become hotter. But this is only taking us down to 8 kilometers. I said there's a deep crustal reservoir at 15 or so. So let's now look at the crystals themselves, the ones that hold the melt inclusions. So any rock you look at, almost any rock you look at, any volcanic rock, magmatic rock, has got zoned crystals. I think of zoned crystals as the sort of mute witnesses to underground upheaval. They are itching to tell us their story. That zoning reflects some change of conditions underground. But what is the story? What are the right questions to ask the witnesses? How do we perform an appropriate petrological interrogation, if you like? And the zoning here, so these are backscattered electron images, and these are plagioclases, plagioclase feldspar, and the different layers, a bit like tree rings, are different contents of calcium, the anorthite component. And we can see the crystals have had a really rather checkered history. This one has grown a bit like tree rings, but this one here seems to have sort of become eviscerated at some point, and some of these are seriously weird. So, but let's just focus on the rather more normal-looking ones. What are they trying to tell us about what happened underground before they erupted? Are they telling us something about that movement of magma from the deep reservoir up the conduit to fuel the eruption? These are all from the 1980 to 86 eruption of Mount St. Helens. So Mount St. Helens is a great place to do this because we actually have a really good database of observations, but also of high temperature and high pressure experiments that allow us to determine how pressure and temperature affect mineral chemistry, mineral proportions, and so on. And this is just a demonstration. We perform high temperature pressure experiments. These are the experiments. We work out what minerals are stable. And in the case of that mineral plagioclase, we establish how its anorthite content, the calcium content, varies with temperature. And we see there's a strong dependence of temperature. But this is a low pressure trend, and that's a higher pressure trend. There's also a dependence on pressure. And in fact, there's an ambiguity in terms of whether it's pressure or temperature. And we're rather interested in both. We don't want to say it's a bit of one, a bit of the other. We want to know how much temperature and how much pressure change they're recording. So here's an illustration of that. This is temperature and pressure. Kind of rotated the axes from before, but think of this now as 12 kilometers, the surface, 860, 940 degrees. These are contours of fixed amount of plagioclase. This is very calcic, and this is very sodic, and this is where it's all melt, and this is where it's all solid. Imagine now we had a plagioclase that was zoned between those two compositions. So that could be due to a drop in pressure. It could also be due to a drop in temperature. So that's the ambiguity. Could be a change in pressure or temperature. What we need is a way to remove that ambiguity. If we lay over other contours on here, those are the contours of plagioclase composition and so on. This is the amount of water in the melt. But the really interesting ones are these blue lines, which are the amount of liquid. So this is all liquid. That's 80% liquid, 60% liquid, 40% and all solid. And these lines are oblique to the ones of feldspar composition. So if you could interrogate a feldspar and get it to tell us not only the anorthite, the calcium content, but also the melt fraction, we could actually resolve this ambiguity. So the difference there is that that zoning leads to a drop in the amount of melt. Conversely, if it's due to temperature, there's no change in the amount of melt. So what we do is we measure the plagioclase crystals not only for their major element content, but for some trace elements, and we use strontium and barium for a variety of reasons. This is a bit of a busy slide, but it's just to show you the method we use. What we're going to do is uncrystallize the crystals. So this is an analytical profile from the outside, the rim, to the inside, and we're going to uncrystallize progressively from the rim to the interior. We're going to make a number of assumptions. We're going to say we know that the system was pretty much closed to inputs from other magmas. Mount St. Helens was. We're going to say we know how the trace elements partition between the crystals and the melt. We should do. I've spent 25 years trying to understand it. We will assume that we can parameterize the composition of the plagioclase from the experiments, how the amount of melt varies with temperature and pressure. It's basically a mass balance calculation. We're going to try and recover pressure, temperature, melt fraction, the proportion of crystallizing plagioclase, and the chemistry of the melt from the rim to the core. So here's a crystal. This is from the 18th of May 1980. There's the core and there's the rim. We measure the anorthite content. We measure from the core to the rim the barium that goes up, the strontium that comes down. We recover from the calculations. We see the pressure in blue. There's a drop in pressure. There's an increase in temperature. There's a drop in the amount of melt. It's crystallizing. There's an increase in the proportion of plagioclase. This crystal is actually telling us its life story from the core to the rim. So now we can take a number of life stories, a number of witness accounts of what happened in the build-up to the 1980 eruption of Mount St. Helens. So this is pressure and temperature. This is now about 13 kilometers. This is the surface. Any one color is a crystal. It started life here. Take the red one, it came down a bit, dropped the pressure, then sank back down to higher pressure, then rose up seemingly rather quickly, not many steps, then spent a lot of time doing something at about 3 kilometers, and then it was erupted. This is the testimony from the crystals. This is the testimony from the melt inclusions that I showed you before in grey. They're completely independent witnesses, but they both agree on what happened in the lead up to 1980. And we can do the same thing over here. This is melt fraction against pressure. What we see again is that important principle. As the pressure drops, crystallization occurs, the melt fraction goes down, the temperature goes up. Crystallization in these systems it leads to an increase in temperature. So the final question then, the final two questions, are, does this agree with the geophysics? Well, there's a whole new project called Mush that is imaging magma under St. Helens, and it's coming up with images of where the magma is. And this is depth here, this is depth below sea level now rather than the surface. There's magma down here and there's magma at shallower level. This is a geophysics image. This is what the plagioclases are trying to tell us. Magma spends quite a lot of time, there's a lot of crystal zones up here. At that depth, these depths correspond, and the magma's had quite a lot of time at deeper levels. These individual crystals are giving us a framework with which to understand the eruptions, the geophysical images of Mount St. Helens. And look at the way the volcanoes behaved from the 1980s to the present day. There's a lot of shallow earthquakes. This is often called the seismic lid. It's the rather fractured rock at shallow level. But every few years, including in 1980 and then in the early 80s and the mid-80s, there are these earthquakes that extend down to, this is 9 kilometers below this point, which is actually already 2 kilometers deep, so it's 11 kilometers depth. We get these little splurges of earthquakes that rise from deep, and I suspect this is magma ascending from depth. If we look over the last month, Mount St. Helens has displayed a number of earthquakes going down to 12 kilometers below the surface. So this looks as though this is the volcano bleeding off magma from the deep reservoir and fueling the shallow system. How long does it take? Well, we can do one more thing with these crystals. We can look at the way the chemical zoning is, and we can ask ourselves, if they spent a long time at high temperature, how much diffusion would have occurred to iron out that chemical variation? And that's what the plot on the right says, but I won't dwell on the details. Suffice to say that the zoning we see in the rims of those crystals has to be less than 10 and probably less than 3 years old. So what happens at volcanoes like Mount St. Helens is that there is a destabilization at depth. Magma rises upwards rather quickly, is stored for a very short time in a shallow magma chamber, and erupts. And I think that provides us with a very nice new framework to start to interpret monitoring signals at restless volcanoes. So thank you for listening, and there are my collaborators.
So again, we have time for a couple of questions if John would like, if you would like to ask them, John. Please, Monica. Microphone, please, for Monica.
Hi, John. I understand why you're using plagioclase because of the zoning. Have you looked at any other minerals? I'm thinking specifically of apatite.
Yeah, that would be a really good idea. So the beauty of apatite is, as well as incorporating trace elements, it can incorporate volatiles like chlorine and fluorine and sulfur and water and carbon dioxide. It also has rather slow diffusion, which is what we want here. We don't want diffusion to obliterate everything. We don't quite know the partitioning behaviour of apatite as well as we do with plagioclase.
Right. Well, on one of your graphs, I don't know whether I misunderstood, but you had the one where you had the pressure temperature and then you overlaid the melt fraction. Yeah. And I was reading weight % water. Is that right? You had percentage of water on one of them. I'm sure.
Tell me when to stop.
That one.
Oh, yeah.
3 weight % water.
Well, only the experts are supposed to spot the green lines on your editing them out. Okay.
I mean, I was thinking, where was the water sitting in the plagioclase? Because
No. Okay. So this is water in the
apatite.
melt. This is what the melt's in equilibrium with. So what Monica's asking is, there's a big difference between 8 and 5 and 3. In terms of plagioclase, wouldn't it be great if we could measure the water in the plagioclase? Then we'd have nailed it. Yeah. There isn't any water in plagioclase, or not enough that we can really measure. But in apatites, there would be. Yeah. So I think the other reason for, I hesitate about looking at apatite is I don't know whether it grew really deep. Plagioclase is great because it's got this deep story locked in. But yes, we should do something with water as well. Yeah.
Okay, thanks very much.
Thank you. Peter Stiles has a question.
Are these all tensile? I don't need a microphone. These are all tensile failure events, are they, John?
Quite catch that.
Tensile failure, not shear events.
Well, that's a good question.
Because we've got fracking.
I was just given a paper the other day that showed that some of these actually have long period characteristics. So these may be related to magma. Actually, trying to match the individual earthquakes, there should be a character in those deep ones that's very different to the shallow ones. My guess is that the deep system is inherently unstable because you've got crystals that are denser than melt, and they're in layers, and the crystal layer is dense relative to the melt, and it sinks. The melt rises up, experiences a drop in pressure, exhales gases. Those gases trigger hydrofractures. That nucleates earthquakes, and then the melt rises up that channel.
I also said that nature was keen on fracking as well.
Yeah, if volcano fracking is, if there's a future there.
Same mechanism.
Okay, any other questions? Okay, thank you, John.
All right, thanks.